Have you ever wondered how satellites manage to stay up in space for, like, decades without constantly firing their engines just to keep from falling? It kind of feels like it breaks all the rules of physics we deal with every single day.
This Reddit user, strong_craft_6990, just nails the confusion, right? My car needs gas, I need food to keep going. Everything on Earth needs constant energy to fight gravity. And yet, you've got these incredible machines, from the James Webb Telescope to your GPS satellites, just hanging out up there for years and years. So what's the deal? What is the secret?
Okay, so the first thing you have to wrap your head around is this. A satellite isn't flying the way an airplane does. It's not using engines to push itself up against gravity. Nope, it's actually doing the exact opposite. It's falling. Constantly.
And believe it or not, the absolute best physics lesson you'll ever get on this comes from a quote by the brilliant Douglas Adams, which was all over the source threads we looked at. An orbit is just the art of throwing yourself at the ground and missing. So how on earth does that work?
Let's use this classic thought experiment to see it in action. Imagine you're on a mountain so high you're basically above the atmosphere. You fire a cannon. The cannonball goes for a bit, then arcs down and hits the ground. Simple enough. Now, fire it faster. It travels way further before it lands. But what if you fire it fast enough? Well, at a certain speed, the Earth's surface literally curves away at the exact same rate the cannonball is falling. It's still falling, but it never gets any closer. It just keeps missing. And that, my friends, is an orbit.
Right, so that little phrase, fast enough, is doing a lot of work here. The concept itself might be simple, just fall and miss, but the speeds you need to achieve this are absolutely mind-boggling. And it's that speed that makes all the difference between a quick trip to the edge of space and actually staying there.
This really gets to the heart of what a rocket launch is all about. A suborbital flight is mostly about going up. You shoot up, you get a few minutes of weightlessness, and then gravity pulls you right back down. But orbital flight, it's not really about up at all. The real goal is to gain an insane amount of sideways velocity so that your falling arc perfectly matches the curve of the planet.
And when I say insane, I mean it. The difference is staggering. According to space.com, a commercial jet is cruising at, 575 miles an hour. A suborbital rocket, like the ones used for space tourism, has to hit around 3,700. But to get into a stable, low Earth orbit, you have to go almost 5 times faster than that.
17,400 miles per hour. Let that sink in for a second. That is the kind of speed you need to be going sideways to fall around the Earth instead of just crashing back into it. It's not some fancy anti-gravity engine, it's just pure brute force speed.
Okay, so you did it. You hit the magic number. You're now in a state of continuous freefall, perfectly missing the Earth every single time you go around. You're all set for the next 20 years, right? Well, not quite. Turns out, space has a few curveballs left to throw at you.
The problem, and there's always a problem, is something called orbital decay. See, even hundreds of miles up, space isn't a perfect empty vacuum. There are still these tiny wispy bits of atmosphere, just stray particles. And when you're moving at 17,400 miles an hour, hitting them creates a tiny but constant drag. And that drag, slowly but surely, saps your speed and your altitude.
And this isn't some abstract theory either. Take the International Space Station. A Reddit user pointed this out. It's flying 250 miles high, but it's constantly running into this faint atmospheric drag. The result? It actually loses about a mile in altitude every single month.
And if you let that decay just happen, if it goes uncorrected, well, the results are pretty predictable. And they can be dramatic. For a perfect real-world example, just look at the last days of China's Tiangong-1 space station before it made its uncontrolled dive back to Earth in 2018.
This chart, which uses data from a research paper that analyzed its fall, shows you exactly what happens. Back in January 2018, it was at about 290 kilometers. By April, just a few months later, it was down to 180. The lower it got, the thicker the atmosphere got. The thicker the atmosphere, the more drag it created. And the more drag, the faster it fell. It's this vicious cycle that always ends in a fiery re-entry.
So if even the massive International Space Station is constantly falling, and multi-ton space stations eventually come screaming back down, how in the world do we have satellites that operate for 20 or even 30 years? Well, it all comes down to 2 key strategies: picking your spot really carefully and giving yourself a little push every now and then.
First off, you've got to pick your parking spot in space very, very carefully.
Down in low Earth orbit, or LEO, that's where the ISS and all the Starlink satellites live, atmospheric drag is a big, constant problem you have to deal with. But if you go way up to medium Earth orbit, where the GPS satellites are, or all the way out to geostationary orbit for TV and weather satellites, the atmosphere is so thin that drag becomes practically zero.
So, for all those satellites that have to live down in LEO, the solution is something called station keeping. They have these tiny, super efficient thrusters, and every once in a while, they just give themselves a little nudge, a little boost, to add back the speed and altitude they lost to drag. In fact, for many satellites, their operational lifespan is basically determined by how much fuel they have for these tiny little course corrections.
But there's an even more clever solution. Find a gravitational sweet spot. And that's exactly what the engineers did with the James Webb Space Telescope. It's not orbiting the Earth. It's parked 1 million miles away at a special place called the Lagrange point. This is a spot where the gravity from the Sun and the Earth perfectly balance each other out, letting it stay put with almost no fuel at all. It's genius, really.
All right, so let's boil this all down. What are the big takeaways here? First, remember that an orbit isn't powered flight. It's just a state of continuous free fall. Second, getting into orbit isn't so much about going up, it's about going sideways at an absolutely ridiculous speed. Third, that pesky atmospheric drag is always trying to pull satellites down, especially in those lower orbits. And finally, we get around that problem by either flying way up high where there's no drag, or by giving satellites little boosts to keep them in their lane.
At the end of the day, an orbit is this incredibly delicate dance between velocity and gravity. We've gotten really good at managing that balance for one satellite at a time. But now, as we're launching thousands, even tens of thousands of new satellites, the question gets a whole lot bigger. How do we manage the traffic, the decay, and the long-term stability of this entire orbital environment? What does that future even look like?